All right, so what I was asked to do was kind of do a review of all of this. Now, here's the problem. This unit just doesn't fit into a nice package, okay? It's got so many bits and pieces to it. So here's the idea, is we're asked to look at a lot of different things. Last unit basically what you did was you figured out the shapes, right? And from that you figured out the polarity, right? Now, what they then brought you over into this unit to do is they said, okay, now we want to look at things like vapor pressure, and we want to look at things like boiling point. And then what we're going to do is also look at solubility, all right? There's a lot going on, but it all falls into a couple of simple boxes, okay? So what you've got to figure out is which box you're looking at, all right? So vapor pressure. What causes differences in vapor pressure and boiling point? The idea is simple. How attracted are things to others of their own kind? All right? So what we've got is we've got a bunch of different, and the other thing they asked you, real quickly, the other thing they asked you to look at is conductivity, which we'll put over here in its own little piece. All right? So, you all right, Mac? So, what we're going to start with is we're going to start with, okay, metals. Okay, metallic things. All right? The way metallic things work is if you've just got one metal, like silver or whatever, what you've got is you've got the nuclei, all right? And you've got the electrons in between. All right? But the thing is, no one particular atom has really any greater or lesser claim to those outside electrons than any other atom. All right? They're sharing them all equally. Why? Because they're all the exact same. Now, you can change that slightly by putting a second metal in there. All right? But again, as long as those metals are just metals, there's not a lot of hold on the electrons. So as far as a metal, it's going to be a pretty stable thing. Now, most metals are mostly malleable. Now, what does that mean? Malleable means you can bend it. All right? Are metals usually able to be bent? Sure. The reason is because, again, this particular one here has no real interest in that particular one there any more than it does one of the others. So if I turn it a little bit or start to move the atoms, they'll shift together and the electrons will kind of just fill in the gaps. Okay? So metals have fairly high boiling points, right? I mean, if you think about it, most of them are metals or solids at room temp, so it is pretty high just to get them to melt, much less to boil, right? They're fairly malleable. They're very good conductors of electricity. What does that mean? That means if I have a battery and I shove some electrons in, that electron is going to repel that electron, but that atom is going to go, I'll take you instead of you, and so the electrons are just going to flow. And so if I'm pushing a bunch of electrons in, these red ones are just going to move out, and the metal's not going to care, because it's still got the electrons it's supposed to have. See what I'm saying? Questions? Okay, next bit, ionic. Okay, now, ionic bonds, straight up ionic. We've got a positive and we've got a negative, all right? And so that positive is going to be attracted to negatives, and that negative is going to be attracted to positives, right? Remember we talked last time about lattice energy. Oops. We talked about lattice energy. How much energy does it take to break this up? And there are two main things. One is the charge, that's the biggie. Should use another color, just not to confuse things. All right? So it's the charge, and it's the size. Charge is more important. Lattice energy goes way the frick up, when we have like a +2 -2 or a +3 -3. All right, so that's the big part of the lattice. Now, is this going to be easily bent? Absolutely not, because this positive is attracted to those specific negatives. It's in a lattice, it's in a grid, it's in that shape that I showed you with the the balls in the thing where it's like one is surrounded by 6. Okay, now are there other shapes? Are there other arrangements? Yeah, but that's good enough for what we need. So this is not malleable at all. Is it going to conduct electricity? Well, if I send an electron in here, all right, that's not going to move. These already have the ones they want, and this specific negative has that negative. It has the electrons it needs. It doesn't want to give it away. So salt or any ionic substance, not conductive, not malleable. All right, not conductive, not malleable, not bendable. Okay, does that help? So far, so good. Okay, now, here's where it gets a tad weird. If I have salt water, right, whatever the salt is, it doesn't have to be sodium chloride, but if I have some salt water, and I have the negatives are swimming around, and the positives are swimming around, and if we get down to the brass tacks, the reason this dissolves is because that negative is attracted by the water's positive part. This marker's done. All right, and this positive is attracted by the water's negative part and gets surrounded by the O bit. Right? That's familiar. Okay, now here's the other trick. So it is soluble. Salts are soluble. The trick is, if I put electricity into salt water, like there's a wire here and a wire here, and I'm trying to make it go out and in, circuit, okay? If I push electrons in this way, what's going to be attracted to the electrons? Positive or negative? Positive. So what happens in the beaker, a little closer up, is if the electrons are coming in this way, the positives are going to flow over toward that. And then the other way, if the electrons are trying to go out of here, then the negatives are going to flow toward that. And so this whole thing, salt water can conduct electricity. All right? Because the electrons can go in, the negatives and the positives can move to keep the balance. Does that make sense? Okay. Now, if we do it, if we push enough electricity in, we can actually get them to do some reduction oxidation. But the main thing is, salts, not conductive. Salt solutions, ridiculously conductive. Okay. That's why if there's a lightning strike, if you're out in the ocean, you want to get out of the ocean, because it's going to conduct electricity really well for a long distance. All right? So good so far. Okay. This will all stay up so you can have it later. All right, now we're talking about the interforces. Intermolecular, I can spell it out if I could. All right, intermolecular forces. And you got the 3 basic types. We'll start from the simplest, London dispersion forces, which are due to momentary dipoles. Everybody can do a momentary dipole. What affects a momentary dipole? If it's longer, you could have more dipole. If it's bigger, in general, you could have more dipole. Right? You get a long chain carbon molecule like an oil. All right? This could have a really high boiling point. You get some of the really big, long chain carbon molecules. For those of you not clear, every place you see a corner when they do organic, that's a carbon. and it's assumed to have all of its requisite hydrogens. So this would be assumed to have 2 hydrogens, this would be assumed, 3 and 2. Okay? Things like this, they have high boiling points. You get like tar. Tar is just a really big long carbon molecule. And since it's long and stretched out, it can have momentary dipoles. And so you can get tar which boils at ridiculously high temperatures. All right? So the only thing that's going to attract one of these to another one of these is a momentary dipole. Right? There's London dispersion forces, that's it. All right? We get down a notch, we can talk about dipoles. Like I said a little while ago, the reason you studied all those shapes and the reason you studied all that polarity crap was so that you could see if it's going to have a dipole. Will it be attracted to itself because of dipole? In other words, like we saw in the warm-up, the carbon, if we have carbon, 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 right, and we have a double bonded O out there, or we have acetone with a C, a couple H's, and a double bonded O. It's not acetone, but it's together somewhere. All right? Then we've got, like you saw in the last chapter, electrons are heading this way, electrons are heading this way. This is dipole neg, this is dipole positive. And so these are going to be attracted to each other very strongly because the one end's negative and the one end's positive. So if you were to see this in a solution, there would be this one would have like this one hooked to it or aimed at it, and another one maybe over here, so that the end that's positive would be near the end that's negative. Okay. All right. Now, right now we're just talking about attracted to itself. We'll get to the next thing in a second. The last choice, of course, is hydrogen bonding or hydrogen attraction. And that's solely when you have hydrogen hooked to with NO or F. And F is just a one-off because the only thing you can have with F is HF. It's the only thing. So really it's when it's hooked to N or O. But they say F because it's one possibility. All right? So then you've got the hydrogen bonding thing like we looked at in the warm-up, where you got the C's with an O with an H. Well, that H is ridiculously positive. Okay? That H is ridiculously positive. And so it attracts to some other O on some other alcohol, right? It would be attracted to that O because that O is pretty strongly dipole negative. Okay. So things with hydrogen bonding are going to be harder to boil than things with, harder to boil than things with dipole are going to be harder to boil than things with just London dispersion. So that's just, yes.
What if you have like tar, just a huge LTF? Could it conceivably be stronger than say one hydrogen bond?
Oh, way stronger. Like some tar or something like that is gonna boil. You know, I mean, you could drive on a road. It can be up over 100 degrees Fahrenheit, and that tar is not melting at all. It's not even melting, much less boiling. Okay, so literally, what they do is, if you go up, if you've ever been up to Philadelphia, if you go up on 95, you're going to see these huge refineries. All right, and what they literally do is they just take the raw petroleum and they heat it, and what happens is the petroleum, they heat it to ridiculous temperatures, and what happens is as it condenses, they gather it, and you'll see pipes coming off of both sides of the tower, and whatever condenses at that temperature comes out as a liquid. And then what's left behind in here are the really long, you know, C20, C30, C40, huge molecules. They don't even boil very well. And so coming out the top, if you ever go by there at night, sometimes they'll be burning off the top because they can't catch the methane that's escaping. And so they just burn it off. They vent it and burn it. All right, they prefer to catch it, but So yeah, those are very hard to boil.
So if you have sufficient blended dispersion forces, because it's sufficiently big enough,
Mhm.
you're able to be stronger than dipole
Yeah,
dipole.
yeah. But I'm saying same basic size. All right, now to dissolve is another beast entirely. All right, what dissolves in what? What is soluble in what? Let me bring one more word. All right, the simple answer to that is like dissolves like. All right, like dissolves like. Meaning, if you are metallic, we're pretty much not worried about they don't dissolve much of anything. All right, but if I'm ionic, it's got negatives and positives. It's going to dissolve in polar things. Polar things are going to dissolve in polar things. Non-polar things are only going to dissolve in, you guessed it, non-polar things. All right, like salt water. Salt water, salt is ionic, polar. This is really important with vitamins, for instance. Okay, most vitamins, you could take a mega dose of a vitamin, absolutely no problem. All right, why? Because those vitamins have some sort of polar nature to them, or they're ionic, possibly, not that I remember, but they have a polar nature to them. So if you take a mega dose of most vitamins, they are water soluble, which means if I take too much, it just builds up, goes into the kidneys, goes into the water supply, and out you go. And if you take mega doses, you're just having really expensive urine, right? Because you didn't need the vitamins, so it just clears your system. The problem is there are about 3 or 4, I don't remember which one, so I won't say, but I want to say it's A, D, E, and K, are the ones that are fat soluble, because those vitamins are non-polar, and so your body can't clear them through the urinary tract. And so what happens is, if you megadose on these, they end up being stored in your fat, because your fat is a long chain, thing with double bond fatty acid kind of thing going on here. Okay, and so your body will store a non-polar thing in your fat. Okay, classic example people always bring up is if you look at certain drugs, certain illicit drugs. All right, if you do marijuana, the THC in marijuana is water soluble. So the THC goes in, the THC comes out. It doesn't stay in your body. On the other hand, if you do, LSD is a big, long, non-polar molecule. So what happens is it goes into your brain, you do your LSD, you get to see, you smell colors and all kind of fun stuff happens, right? All right, that's great. And then it can possibly, and they've shown this actually works, it'll actually get stored in the fat of the brain or somewhere else in the body. And if it breaks loose again, here you are, your mother of 2, 40-year-old driving in your minivan, and all of a sudden, the elephants, man, they're back, yo! What are they doing on the highway? Okay, that was a bit much. All right, but no, that's the thing. Some of these drugs are actually stored in your body, and you can't clear them unless that fat clears, and they're there for good. Okay, so that's the solubility thing. All right, one more piece to the solubility thing. Can we dissolve non-polar things in water? A little bit. Good thing too for the fishes. Why? All right, what's dissolved in water that the fish use? Obviously, oxygen. They're mammals. No, they're not mammals. They're fish, but they're animals, so they need oxygen, right? So you can dissolve a gas in a liquid a little bit. But here's the trick. This is about the last thing. So if you zone back in for a minute. All right. The trick is how rapidly, if this is water, how rapidly is the gas moving above the water? Pretty fast, right? Many degrees of freedom, mesh motion. True? So if it's over here on the surface and we want to get it to dissolve, what do we have to do to it? We have to either push it in or we have to slow it down. Okay? To get a gas to dissolve in a liquid, we have to slow it down to get it in there. So to get a gas to dissolve in a liquid, we want it colder. Or we can pressurize it. That's why when you open your bottle of soda, it makes that neat little noise. Why? You know, and if you watch closely, if it's a clear bottle, what you'll see is you'll actually see bubbles. All right, in the liquid. All of a sudden, there'll be a bunch of bubbles that will appear in the liquid. Because that gas is dissolved in there, and what they do is they pressurize the heck out of the headspace below the cap that forces those gases to stay in there. It keeps them in equilibrium so they're trapped in the liquid state, inside the liquid dissolved. And as soon as you unpressurize the top, they are able to escape. All right? If you want them to stay in, you've got to make them really cold. Now compare that if I want to dissolve an ionic substance in water, if I want to dissolve sugar or salt in water, sugar's its own case, but if I want to dissolve salt in water, what do I got to do if I want more salt to dissolve in the water? What?
You just put more in.
Put more in to a point. When I put enough in, what happens?
Saturation.
You get saturated. Did we talk about chocolate milk?
Yeah.
Okay, so if you put enough chocolate into the milk, you get saturation. If you want more chocolate to dissolve in the milk, what can you do? Heat it up. Because these guys are very slow, and these guys have more freedom. So if we want more of these to get out, we got to get them moving faster to get up into the liquid phase. That's why if you go down south, you get sweet tea. Because what they do is they put the sugar in when it's wicked hot or while it's boiling, and some of that stays super saturated. So you get extra sugar into your tea. Yeah, exactly. All right? All right.